Well, good evening. We're back again at the HAM class 2025 Amateur Extra. Tonight we're working on Chapter 6 in the ARRL Extra Class License Manual. We'll be finishing up the chapter tonight. We did the first half last week, and we'll be wrapping it up tonight. So one of the topics, actually the first section, 6.3, is about digital signal processing and software-defined radio, or SDR. That's relatively new in the license manual. It's been there for a couple of years. The other two sections, filters and power supplies, they've been around forever, but it's all core material, so I think you'll enjoy going through it, at least for the sake of getting through the pool questions. So we'll start out with digital signal processing. Now, SDRs and digital is really much of the current radios being produced, and just about all new radios are going to be in that, using that technology. The specialty radios accepted, like QRP and so forth. So we're going to be touching on principles and tying them to the pool questions. Jump right into the deep end here. Digitizing an analog signal. Now down we have here on the bottom is a sine wave, and all of these little red lines are samples. So if these were happening one millisecond apart, at time plus 1 millisecond, we're going to take a snapshot, and we see that the sine wave is at this particular place. 0.4 of a volt, we'll say positive. So we're going to take that snapshot and save that number. 1 millisecond later, we're going to take another snapshot and get this value. It looks like it's about maybe 5 or 0.6 of a volt. And we go on and on all through the sequence. So you can see that we're taking pictures of this waveform all the way around. Now there's a lot of advantages to processing signals digitally. Get better quality. Features are easier to implement. It's easier to modify software. But we have a slight problem being humans in that we cannot speak ones and zeros. So we have to have analog to digital and digital to analog conversion happening. We see that up here in the diagram. So we start out with an analog signal. We use what's called an anti-aliasing filter, which we'll be talking more about. And then this sample and hold circuit, you can see that we're closing it for a very brief time and taking the picture to get these voltage values. And from there we go. Now we're analog on this side, and the analog to digital converter puts us into the digital domain for all of the signal processing that we might want to do. That can be filters and modulation systems, encoding and decoding, just everything you can imagine can be done digitally. And then we come out of that after the signal processing, back digital to analog converter, so that us humans can understand what's going on. Reconstruction filter, and then back to analog signals. So that's a high-level overview of how digitizing works. Just a quick little side note here. We're not going to get into binary counting, but some people have wondered how this works. So as we're taking these snapshots of the voltage waveforms, the values of the sine wave, we're converting them to numbers. I mean, the numbers work like this. We understand 1 through 15. Binary, each one of those numbers represents something in this case, a 4-digit binary number. So it starts out with all zeros. And then the first number, which you could imagine would be 1, but since we only have ones and zeros, we now have to carry the 1 here, and that's what becomes number 2. So that process continues on all the way up to the number 15. This is just a simplified example. If this is something that you're interested in, there's a really excellent tutorial here that I'll refer you to. It's just a little sidebar, what's going on. Everything has to be in ones and zeros to be in the digital domain. So some more considerations now for sampling as we build on what we've talked about. First of all, the Nyquist sampling theorem is central to everything that's done in sampling. And it states, and this is in blue text, sampling needs to be at least twice the rate of the highest frequency component of the signal. So that's important to remember. So when we get into anti-aliasing filters, that's going to play a part. This particular diagram, we're showing about 10 samples in a full cycle. Okay. So if this Nyquist sampling theorem is to be observed, that means we'd only be able to sample a signal with a maximum frequency of 5 hertz. So that wouldn't be very practical, of course, but they're just showing this for illustration purposes. Now, in the audio world, if you have a CD player, I guess those are becoming obsolete, but the speech or the frequency range is usually 20 hertz to 20,000 hertz. So you'd have to be sampling at least twice that, or typically it happens at 48 kilohertz for audio on a CD. So our radios go from, let's say, 160 to from 160 up to 10 meters, so you can see we're dealing with higher frequencies there if we're going to be talking about sampling right at the RF frequency. So we'll get into that a little bit more. Now, the reason that the Nyquist sampling theorem is important is that false signals will be generated if sampling is slower than 2 times. Those are called the alias frequencies. And we'll have a diagram of how those work coming up. So it's important, if we're going to be digitizing something into the front end of a radio, that we make sure that the frequencies above what we're interested in are being filtered out. And that's done with an anti-aliasing filter to make sure that we're going to keep our digitized content at less than 2 times our sampling frequency. And then here's kind of a strange thing. A small amount of noise called dither may be added to the input signal to reduce quantization noise. Now, what in the world is quantization noise? Well, we saw here that we're just taking samples every so often. Well, the signal is progressing in between those samples. So results from not sampling it many more times than what we're showing here is called quantization noise. And it's just a technical thing. It's very mathematical if you want to really understand what this means, but for the purpose of our pool question, we just need to know this as a fact. A little bit more on what is an alias. Well, here is a signal, a sine wave, and these little dots that we're seeing here, these are the samples. And you can see that there's, so over about 10 cycles of the waveform, we're only sampling about 9 times. So we're way under the 2 times sampling required. So let's see what happens with a reconstructed waveform. We're going to be doing this on purpose to create an alias signal for illustrative purposes. So this point here corresponds to here on the bottom graph. The next point is up here. You can see that it corresponds. So every time we every time we do the sample and then plot it, you can see the waveform that results. So even if this was smoothed out, you can see that this would have no resemblance whatsoever to the waveform that we were trying to sample. So this is what happens if we wind up with false signals or aliases, or maybe that'd be alii or aliens or something. But here you can kind of see why that's a problem. Now the reconstruction, you can see once we do have a sampled waveform, the output is still pretty jagged. And because it's not smooth, the pieces that we're missing are the quantization error that we talked about. So we can get pretty close to the original, and then we can use a filter to smooth it out. So here we've got a picture of a low-pass filter. Low-pass filter is used at the output of a digital to analog converter that removes the spurious sampling artifacts from the output signal. You may recall that square waves or stair steps like this, they have very fast rise times. So you wind up with a lot of RF noise that's well above the frequency that you're trying to reconstruct. So if that's filtered, you can get this representation. It's kind of a funky looking sine wave, but I think you get the idea. So that low pass filter is important at the output of an analog, digital to analog converter to get rid of those artifacts from the output signal. Now there's a term here that is very confusing, and they use these terms interchangeably in our pool questions. So these terms are all roughly equivalent. Okay, so we're going to consider 4 bits or 4 steps in our stair step, 5, 6, up through 10. I've highlighted or put a couple of them in blue because they show up in pool questions. And you can just remember that 8 bits will give you 250 steps of resolution, and 10 bits will give you 1024. It would be helpful to know that. Now, the terms that are applied, I put down everything I could think of here, and now these all mean the same thing, all right? But they're worded differently in our pool, so didn't want that to trip you. The number of input levels, okay, corresponds to the number of bits that we're sampling, or the number of bits, sample width, sampling resolution, bit depth, steps, and precisions. These are all words that pretty much refer to the same thing. So how can we prove to ourselves that, let's do 2 to the 10th power, for example. I'll do that on the calculator. It's not something that you need to do, but if you can't remember that 2 to the 10th power is 1024, you could use the calculator to figure that out. So I'll step over to the calculator and turn it on. First thing we always do is clear. So there's a function we haven't used before. It's this x raised to a box. So I'm going to, I'm going to do this the hard way first. How does that sound? 2 to the 10th power is going to be 2 times 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 2. Now if I didn't mess that up, I'm going to get 103 raised to the third times 10 to the third. If I press the answer toggle key, I can see that we got 1024. So that's the hard way to do it. I could multiply 2 times itself 10 times. The easy way to do it, if you ever choose to do this, I'm going to clear this, is to use this function, x raised to a box. I'm going to do 2, x raised to a box, 10. You see how that appears? 2 to the 10th, enter. Press the answer toggle key again, 1024. So that will work. If you need to know what the number is and you can't remember or you haven't memorized it. The other one that we're going to be concerned with is 256. All right. So there is a question, how many different input levels can be encoded by an analog to digital converter with 8-bit resolution? That's our 2 to the 8th power, 256, which you can probably just remember from our chart, which is fine. But I wanted to show you how to get there. Now this is the trickiest question in the whole chapter, I think. But if we walk through it one step at a time, I think it'll make sense. It asks, what is the minimum number of bits required to sample a signal with a range of 1 volt at a resolution of 1 millivolt? All right, so we're going to have a maximum of 1 volt, but we need to be able to determine the value of what we're measuring to the 1,000th of a volt, or millivolt. So there are 1,000 millivolts in a volt, so we need a bit depth that will give us at least 1,000 steps. Okay, So it turns out that 2 to the 10th is 1024, so we will need 10 bits in order to resolve any voltage between 0 or 1 millivolt and 1 volt. So hang on for now, we'll see this again. Hopefully that walkthrough will at least seed the concept for you. Now there's several questions that they scrambled the words, I think, just to help confuse us. What sets the minimum detectable signal level for a direct sampling SDR receiver in the absence of atmospheric or thermal noise? That's the question. And the answer is it's determined by the reference voltage and the sample width in bits. Now you're probably saying, what in the world are you talking about? Well, remember this thing that we just saw over here? Minimum number of bits required to sample a signal and so forth. We knew what the reference voltage was here. It was 1 volt. And we wanted to be able to resolve down to 1 millivolt or anything in between. So with that, I'm hoping that this will start to make a little sense. What sets the minimum detectable signal level for a direct sampling SDR in the absence of atmospheric and thermal noise? Now, the reason they put atmospheric and thermal noise in here is because that can be well above the sensitivity threshold of the receiver. So hopefully this now connects. Okay, the minimum detectable signal level determined by the reference voltage and the sample width in bits. So if the maximum expected input was 1 volt, that would be the reference voltage. If the sample width in bits was 10, that would yield 2 to the 10th or 1024 steps. So the minimum signal that could be detected would be 1,000th of a volt or 1 millivolt. Just kind of reconnecting this in all different ways for you. The wording is very confusing, so I wanted to go over that from a couple of different angles. All right, well, what about the quality of an analog to digital converter? We saw that we had quantization noise or error, so some distortion is going to result. And what measures that, the way of measuring it, the quality of the A to D converter may be measured by total harmonic distortion, excuse me. So we have an analog input, we have an analog to digital converter, we have a digital output, and then digital analog coming out of the digital domain, coming back into analog, and then we check the total harmonic distortion to see how bad it is. Now this is pretty mathematical. If you want to go beyond that simple description and the factoid that they're wanting us to know, I did put a link in here that gets into great detail on how to do that. You might have heard of total harmonic distortion in terms of your stereo equipment, because that's a major specification for stereo equipment. They want that to be super low so that you can hear all the nuances between the violins and the cellos and the flutes and so forth. That might be where you've heard this term before. Now we're going to talk about Joseph Fourier. It's really interesting because some of the scientists that came up with the principles that we use in radio came up with their math way before we had radio. But it's foundational and critical to radio. So he was a French mathematician, died in 1830, and he proved that a square wave is made up of a sine wave plus all its odd harmonics. I'll show you a little picture of how that works out for us. And then much later, in our current century, somebody figured out how to simplify the fast Fourier transform that he came up with, or the original version of it, and they came up with what's called the fast Fourier transform, or FFT. And that's extremely important because our digital displays on our radios, our waterfalls, our spectrum displays, all use this function. Convert signals from the time domain to the frequency domain. And I'll expand on that a bit too. So here he was, handsome devil. And if you're really geeky, you can actually get a t-shirt for one of your ham buddies, I don't know if you get it from Amazon or where, but if you're really geeky, you could buy one of these for your ham friend. I don't think the girl comes with a T-shirt, but you can get the T-shirt. Okay, here we're getting into a little bit more on time versus frequency domain. And time domain is what you see on a regular oscilloscope. It's voltage vertically and time horizontally. And then in the frequency domain, we're showing, instead of time on the axis here, we're showing frequency. So let's see how that starts to add up. Notice that we're getting something that's starting to look like a square wave over here. Remember, we said that a square wave contains all of the odd harmonics. So here's the fundamental. Here's the second harmonic, the third harmonic, and as we mix these together, the resulting waveform starts to approach a square wave. And if we kept going, it would truly be a square wave. So we have time going in this direction, and then we've got frequency going in this direction. So if you were to look at this on a spectrum analyzer, you would see these blips. If you were to look at the same signal on an oscilloscope, you'd see something that looked like a square wave. So that's central to something that looks very familiar to anybody that has a radio that's probably been made in the last 10 years. This is an ICOM 7300, and here we see it's on 14200.88, that's the center, and then it's showing plus or minus, it looks like 25 kilohertz. So you can see these signals up and down the band. Sideband, remember that's 3 kilohertz. So they're kind of wide. In CW, they just look like little spikes. Here's a CW frequency. So this is something that is very handy in our modern radios. If you were doing contesting, for example, and you were doing search and pounce, you don't have to spend a lot of time dialing up the band listening to noise, right? You can see that there's a signal right here. And the way most modern radios work, if you just click on this line or touch it, the radio automatically tunes to that frequency. So you can go right to something that you see on the spectrum display.
And I just want to clarify, that is a frequency domain display.
Yes, right. Shows frequency, in this case, relative to a center, up and down. Now we're going to jump into another concept. We have a lot of things to tie together tonight. Digital decimation. So what is the function of decimation? Well, it reduces the effective sample rate by removing samples. You're probably wondering, well, why in the world would you want to do that? It sounds totally crazy. Well, you know about mixers, right? We've talked about mixers where we've got an incoming carrier, incoming signal. We mix it with a local oscillator and wind up with an intermediate frequency. Well, the same thing can happen in the digital domain, and here we're talking about megasamples per second, and we're concerning a frequency of 14.300, and we're sampling it at 100 megasamples per second. And then we have what's being called a local oscillator here. It's actually generating a digital signal, but the difference between this sample rate and this sample rate winds up as 3 kilohertz at 100 megasamples per second. Now that's still way more samples than we want to deal with. So a digital decimator will take 1 out of 1,000 samples and reduce this by a factor of 1,000. In this case, it gets us down to a 3 kilohertz audio sampled at 100 kilosamples per second, which is a lot more reasonable. So that's the concept of decimation. We're taking a bit stream and taking samples out, which is roughly equivalent to analog mixers, but in the digital domain. Well, what if we wanted to go the other way? Well, that process is called interpolation. Well, in the case of interpolation, we're going to add samples to increase the bit rate. We'll see how that works coming up as well. Now we're going to tie a couple things together here. An anti-aliasing digital filter is required in a digital decimator to remove high-frequency signal components that would otherwise be reproduced as lower frequency components. So even though we're showing here a 3 kilohertz audio sample at 100 kilosamples per second, there's some amount of stuff that has leaked through from all of this. So we put an anti-aliasing filter here so that we're not passing any higher frequency content on to the next stage. So that's one use of an anti-aliasing filter. If we did pass those higher bit rate samples through, or some of them snuck through, they would create aliases in the signal chain to follow. Well, let's see if this makes sense now. Yeah, it's like we're using it basically as a low pass filter. Now, DSP systems can happen any place in a radio chain. So we're showing analog signal in, analog to digital converter, and then digital signal processing, or DSP. So here we're analog. Now in this, here we're digital. And then when we're done processing the data, demodulating a signal, for example, or doing a notch filter, whatever digital functions you're interested in, then we convert it from digital to analog to get the analog signal out. So this is a generic DSP system. In a radio, this can happen any place. We can actually sample right at the RF frequency, some of the newer radios. Before folks were doing that, because of all of the advantages of digital signal processing, they were going through a couple of stages of analog mixing because the digital signal processing has a hard time working at very high frequencies. So typically it's mixed down to an IF that is better suited to digital signal processing. Applications are notch filters, bandpass filters, noise filters, demodulation, and just all kinds of things you can do in the digital world. A lot of alphabet soup going on here. ADC, DSP, DAC, but as you see those, hopefully they'll connect. So what kind of information can be processed? Well, just about anything. You know, look at this list and much more. And for our alphabet soup, ADC converts analog to digital conversion, and DAC converts it back. This is just all background. An amazing thing about using digital processing to analyze a signal, I'm thinking in terms of FT8 right now. It's possible with an FT8 signal for you not to be able to hear it at all. You might hear just pure noise, for example. But with digital signal processing and integrating what's coming in over time, they can actually put together this original waveform, even though it's completely in the noise. So that's a trick that you can do with digital that we never could do before. And here's a block diagram, putting a little bit more meat on the bones here. So this is a case where we're doing some conversion up front. I used a Yaesu FTDX 1200 for a couple of years. It was our main HF radio, and it works this way. It's actually a triple conversion receiver, so there's 3 stages of mixing that are happening before we get to the digital signal processing area. And down at the bottom it says this part can be done in a computer. So once we've gotten the signal down to a level that we can deal with, frequency-wise, then this is like the previous slide, one of the previous slides we showed, analog to digital. Then we do our analog or our digital signal processing. All of those wonderful functions that can be done, convert it back to analog audio amp, and then we can hear it. So this can happen basically any place we've been talking receivers in the receive chain. So this can be done in the radio, or it can be done in a computer. That's another nice thing about software-defined radios. You don't necessarily have to have knobs on the radio, because a lot of these functions can be done on your computer by feeding it a data stream. But I'm getting ahead of myself. So we talked a little bit about modifying data stream rates, and I showed you a diagram. So decimation, that reduces data rates by removing samples. And they don't really have anything on going the other way in the pool question, so just remember this one for now. So decimation, when you decimate something, you could think of blowing up a building or something. You blow it to bits. You're removing bits from the data stream in this case. Also called down converting. We're going to be seeing digital down converters coming up, kind of the equivalent of analog mixing. And a decimator requires an anti-aliasing filter to remove high-frequency components. We said that already, but just trying to put it all in one place for you here. Interpolation is going the other way, so where we're taking bits out, here you can see in a decimator, we're basically skipping every other bit. For interpolation, we're adding bits into the stream, which is the reverse process. It's like mixing up in the analog world, also called up converting. And we can multiply a signal up to a carrier frequency. But they don't ask us about that in the pool. Now, before we get into sampling, we want to make sure that we're only, our sampling circuit is only seeing signals that allow us to, our sampling rate to be at least double the sampling rate. So a low-pass filter is used in front of that sampling process, part of an analog to digital conversion, also used in digital decimation, tying more pieces together here, ensures the input signals do not exceed twice the sampling rate. So here we're going to cut off those higher frequencies here. We only want to deal with these. And when we're doing it this way, it's called an anti-aliasing filter. After digital to analog conversion, an anti-aliasing filter is used to remove spurious outputs from the digital processing, so it won't confuse stages that follow. Smooths the output waveform. When used that way, it's referred to as a reconstruction filter. So a lot of terminology here around just a couple of basic concepts. A little bit bigger view of our filter. We're going to be talking about filters after our break. Reference point is 3 dB. So when we're down 3 dB from anything here, you can see that's referred to as the filter cutoff. Now I put a link here, passive RC filter tutorial. If you want to see more about how you can do all different kinds of filters with RC filters, this gets into it in some depth and very much relates to what we talk about in the chapter. If you want to go further. Supplemental information. We already talked about the concept of a low-pass filter, smoothing the waveform, and right into some questions. So you should feel pretty smart now because you'll be able to answer all of these. So you can unmute to give us an answer, and remember the 3-second rule. How frequently must an analog signal be sampled to be accurately reproduced?
Bravo.
It is bravo, at least twice the rate of the highest frequency component of the signal. What is the minimum number of bits required to sample a signal with a range of 1 volt at a resolution of 1 millivolt?
Delta.
That is delta, and you probably remember that. I kind of walked through why that was the case, but if you can just remember it's 10 bits, you got the answer. What sets the minimum detectable signal level for a direct sampling software-defined receiver in the absence of atmospheric or thermal noise?
Bravo.
That is bravo. Reference voltage level and sample width in bits. You're doing great. What is dither with respect to analog to digital converters?
Bravo.
Bravo. We're liking bravos tonight, aren't we? A small amount of noise added to the input signal to reduce quantization noise. Why that works is really mathematical, but just accept it as a fact for now. How many different input levels can be encoded by an analog to digital converter with 8-bit resolution?
Delta.
Delta. And you probably remember that, but you could also do 2 times 2 times, you could do that trick if you didn't remember. What is the purpose of a low-pass filter used at the output of a digital to analog converter?
Charlie.
It is Charlie. Remove the spurious sampling artifacts from the output signal. Which of the following is a measure of the quality of an analog to digital converter?
Alpha.
It is alpha. Now these seem real easy after going through those explanations, which is good. I want you to be able to answer the pool questions. What function is performed by a fast Fourier transform? Might have to think about this one a little bit.
Charlie.
It is Charlie, converting signals from the time domain to the frequency domain. Or it might be frequencies on a radio that you see displayed by frequencies in the spectrum display that I showed you. What is the function of decimation?
Delta. Bravo.
It is Bravo, reducing the effective...
Yes, it is reducing.
Yes, okay, well, you got it now. Reducing the effective sample rate by removing samples. Kind of blowing up the signal, so to speak. Why is an anti-aliasing filter required in a decimator?
Alpha.
It is alpha. It removes it removes high frequency signal components that would otherwise be reproduced as lower frequency components. So that would be on the front end of the decimator. And you can also use an anti-aliasing filter at the output. It's not in the pool here, but to eliminate anything that might sneak its way into the following stage. All right, now we're getting into software-defined radio. This is such an exciting thing. Let's see where this takes us. We're only going to scratch the surface here. So if you thought you'd be able to design software-defined radios after this class, you're going to be disappointed. But we want to catch some highlights at least. So here's some modern ones. The ICOM 7300 is an SDR. The Flex 6600. You still have yours, right, Gary?
Yep.
Yep. Anon is another brand. Yaesu recently came out with the FTDX 710. These are all SDRs. So what is a software-defined radio? A radio whose functionality can be altered by software, which is kind of nice because updates to features or bug fixes can all happen with downloads. Replaces the traditional analogs with digital signal, traditional analog circuits with digital signal processing. And there are 2 flavors, really, of SDR. There's what I like to call it radio with knobs, like the 7300, or a radio without knobs, like the Flex 6600. You don't see any knobs on this radio. They have something called a Maestro that can be interfaced to it, or you can run it from a computer. So those are the 2 flavors that we have today. Now, because these are digital, you can, I mentioned a computer, you can also control these radios from, well, a laptop obviously is a computer, or an Android device, or an Apple device, believe it or not, can be used to control these radios. And this link, SDR Control for ICOM, points directly to a page that shows the ICOM software that's available to use on those other devices. But if you go to the home page at this location, it'll bring up links for other kinds of platforms, such as Apple or others, Android. Very interesting concept. Control your radio from your smartphone. So here's a picture of ICOM's version of their software. Okay, here's what you see on the display. Their BA1 version 2 software. This is a different product than the one I showed you in the previous link, and you're running this, aren't you, Gary?
Yeah, I have this. I have another bit of software that's free called WF View. Both run on a Windows machine and can control my ICOM 7760.
Right. So this particular software will work across all of the ICOM families, or as Gary said, there's other alternatives out there as well. And it looks just like the radio, but it's on your computer. So let's take a few minutes and look at an SDR radio block diagram. Looks like a lot of confusing stuff here, but we'll kind of walk through the transmit path and then the receive path and comment on it. And it's digital all the way through. You'll see at the antenna on the receive side, we're converting it directly to digital right at the antenna, which is never used to be able to do that before. It used to be that any digital signal processing had to happen after analog mixers. It goes through all of this interesting stuff here and eventually winds up out at the speaker. In the other direction, the transmit direction, the microphone goes through some fancy electronics and winds up at the antenna. So we're digital every place in between. Now getting into some of the detail here. This diagram, if it's hard to read on the screen, this is on page 6-31 of your book, if you care to follow there. So the first question, we already alluded to this a little bit, why SDR? Almost any kind of signal processing can happen in this digital signal processing. Modulation, demodulation, filters, frequency synthesis. Functions may be altered in software with updates from the manufacturer. It achieves all of the magic of digital signal processing that we just talked about. And this might be what's driving the industry. Lower parts count. You don't have all of these analog mixers and filters and all of that, because it's all happening in software. So it's lower parts count, and if it's lower parts count, that means that the build cost is going to be lower. Now, that doesn't mean that these radios are necessarily cheap. I think we're paying for all of their development costs and so forth, but these are all advantages. So there's kind of two phases that we're going to be talking about as we go through the rest of this. Talk about the transmit path first. Start out at the microphone, analog to digital. Then we go through some things to get a pair of signals called I and Q. And I've got a couple slides that just touch on that a little bit. Basically what's happening is we're creating a 90-degree phase shift in a pair of signals here. That 90-degree phase shift is really, really magical because it's what makes all of this DSP stuff work. So we're in the transmit path. We're at a relatively low frequency here. We've got a DUC, digital up converter. So we're going to be doing the interpolation function there to get this multiplied up to a carrier frequency. We're going to convert these I and Q signals then up to the point where we can apply a carrier out to the antenna and transmit. So that's a super fast description of what's happening. The I and Q signals, by the way, are called the in-phase signal and the quadrature signal. We haven't discussed that yet, that's coming out, but it's basically signals that are 90 degrees out of phase with each other that enables all of this magic to work. Back to where I need to be. Okay. In the receive path, we see some very similar things happening. We have an anti-aliasing filter before we do this conversion for the reasons we talked about. This little block is an automatic gain control. If you're getting signals that are way too strong, that can be detected here and can be turned the level down, so to speak. So that's what this is about. We're going to convert from digital to analog and go through our I and Q signals. We're going to decimate. This is a digital down converter, going from the carrier frequency down to something that we can deal with more effectively with the digital signal processing. We wind up converting back to analog and listening to it in the speaker. So that's the receive path. Again, we're just touching the highlights here. Some blue text for you. Digital sampling and software-defined radios. Incoming RF is
Direct sampling.
direct sampling. Thank you. Yes, direct sampling in software-defined radios. Incoming RF is digitized by an analog to digital converter without being mixed with a local oscillator signal. So there's no analog here at all. So we've repeated that here. Direct digital conversion, DDC. And I put a little picture in here of a product that you can buy if you wanted to play with direct digital conversion. This product, the SDR Play, the RSP1B, is the current version of the product, and this will take you to their website. This is about $139, so you can get into a pretty high quality receiver in the digital world. You notice there's no knobs here. This company also has software that runs on your computer, so that this is a good way to play around.
These radio receivers are exceptional.
They're very, very good. Yep. And the RSP1B is an improvement over the 1A. Gary and I both have the 1A. I don't know if you bought a 1B yet or not, but
No.
they're similar. So remember this, sample rate determines the maximum received bandwidth of a direct digital conversion SDR. A couple of things we've already talked about here, just getting them all in one place for you. Now, we talked about sampling as a method to get us from a signal into the digital domain. There's two additional ones that are mentioned just very briefly, and they do show up in the pool. One I'll comment on is called flash conversion, and the other one is successive approximation. I wanted to comment on this because we saw when we were talking about comparators, when we were looking at op amps, and I thought you'd be able to relate to this. Here we've got a signal coming in, V reference, our reference voltage, and notice this resistor chain. So each one of these comparators is looking for a slightly different level of signal input. And when it detects that, it will provide an output. The output of the output will switch, and we can use a couple of gates here. And this whole circuit winds up being a 2-bit flash analog to digital converter. I thought you could relate to that from our discussion on comparators. Another method is called successive approximation, and it's just another type of analog to digital conversion. You only need to know that as a fact. If you want to have some more insight on how that actually works, which will make your head explode, these are two Wikipedia articles that get into each of these in a little bit more detail. What you need to know is that flash conversion, very high speed, it allows digitizing high frequencies. I can't talk tonight. Successive approximation is just another type of analog to digital conversion. So we don't need to get into the detail. Now, what is this up here? This is a KX3. I've got one of these, and it's an SDR with knobs. Just another example of an SDR. Now we're going to get into those I and Q signals just a little bit. We're just going to skim the surface, though. There's so much more that we could get into here, but they're terms that you're going to run into all the time in software-defined radios and digital signal processing. So it depends on mathematical processing of the in-phase signal, and one shifted by 90 degrees, which is the Q or quadrature signal. So by creating that phase shift, it enables all of this magic to work. And then there's a mathematical function called a Hilbert transform. It's a digital signal processing filter used to generate an SSB signal. So this is how we generate single sideband digitally, without all of the methods we've talked about previously. This would be the phasing method, which we did talk about. So single sideband may be generated by combining signals with a quadrature phase relationship. Those are the I and Q signals we talked about, the in phase and the quadrature signal. And we're just dealing with facts here. You don't have to recreate this. And then our fast Fourier transform we talked about. It's a process applied to the I and Q signals to recover the baseband modulation information. So this all kind of plays in together. It's all math, it's all magic, but it works fabulously. And here's this good-looking fella, David Hilbert. He's a little bit later, died in 1943, German mathematician. Now you can tune out for this next slide if you'd like, but I wanted to make some connections to some things we talked about before. Remember when we were talking about complex impedance, we had an imaginary axis where we put the reactance value, and then a real axis where we put the resistance value. Well, complex numbers come back to haunt us here, except we don't have to do any calculations. I just wanted to give you the concept. So here we've got our 90-degree phase shift. The real axis, or x-axis, is where the in-phase signal is plotted, and the quadrature channel, or the Q signal, is where that one is plotted. The signal winds up in some place in these coordinates. You don't need to understand all of this, but I just wanted to make the connection to complex numbers and something that we had already seen before. So that this is what's necessary for all of that magic to work. Now here's a complete block diagram. We've already, I think, touched all of this, but this one is showing the I and Q signals where they appear and get recombined, how that applies. And like I said, we're just scratching the very, very surface. Really cool stuff. Go a lot deeper. And right into some questions. So what is meant by direct sampling in software-defined radios? A lot of words to read.
Charlie.
It is Charlie. Incoming RF is digitized by an analog to digital converter without being mixed with a local oscillator signal. That's what direct sampling is. We're sampling directly at the antenna. What aspect of receiver analog to digital conversion determines the maximum received bandwidth of a direct sampling software-defined SDR? Now this one, you're going to be tempted to pick the wrong answer, but read how the question is set up. It's asking for the maximum received bandwidth. I don't know if I heard it there, but it is alpha sample rate. Now the sample width in bits, that's what we talked about in terms of the minimum discernible signal.
And that's the one I said.
Yeah, very good. So this one here, maximum received bandwidth. I don't know if I don't think I commented on this, but you can see an entire ham band on a spectrum display. And the amount of signal that you can see is determined by the sample rate. And what's really amazing, I'll just do a brief sidebar here, it's possible to sample huge swaths of the spectrum. I don't remember what the what your radio, the 6600, that'll do multiple groups of frequencies at the same time, or will it do the whole ham band?
It'll do close to the whole ham band.
Yep.
I think it's about a 20 megahertz bandwidth. I don't remember exactly,
Yep.
but yeah. So the sample rate, if you're going to sample the entire HF spectrum of up to 30 megahertz, let's say, well, then the sample rate has to be at least twice that,
Yep.
60 megahertz or greater,
Yep.
and so that's what sets the bandwidth of the ability to receive, whereas the bit depth is the amplitude.
Yes, exactly. That's why this one is a little tricky. I'll make one more side comment as well. In some of the major contests, the contest sponsors are now recording the entire contest and the entire bandwidth, all of the ham bands. So if you're cheating in a contest, they can go back and listen, see what's going on. So another application of some of this technology. Little sidebar there. All right, back to the questions. Which of the following is a type of analog to digital conversion? We talked about 3.
Alpha.
Alpha, successive approximation. Yep. We had direct sampling and flash conversion were the other 2. Why are direct or flash conversion analog to digital converters used for a software-defined radio?
Delta.
Charlie.
Well, it is actually Charlie. Yep, very high speed. We talked about the comparator circuits, and they don't have to think very hard. They just have to decide, well, is this voltage above or below a value in order to do that sample. So they run really, really fast. These kinds of things are often the very front end of a software-defined radio, where the first level of conversion happens before it's down converted. So very high speed. Allows us to work at RF. What type of digital signal processing filter is used to generate an SSB signal?
Charlie?
It is Hilbert, the Hilbert transform filter. Which method generates an SSB signal using digital signal processing?
Delta.
It is delta. Yep, it's that magic of the I and Q signals, quadrature and phase relationship, or direct and I and Q signals. All right, and we're doing great for time because we just did a lot of really hairy stuff. I'm going to take our break at this point, and then we'll come back to the to filters and power supplies after the break. So this is a well-earned break. We covered a lot of heavy stuff in this first half. So yes, we'll see you back in 5 minutes, I hope. Okay, we're back. Hopefully you did something to get your mind off some of this, but we will be changing topics here, so you can let everything we talked about before sink in a little bit. Filters and impedance matching. These are principles that have been around from the dawn of amateur radio, but they're still central to much of what goes on in our radios and our antennas, and we'll be getting into it. We'll be talking about analog first, and then we'll extend the discussion to include digital filters after that. So here's a filter. I stole this from Dave Kassler, but it's really good in that this is how radio filters work as well.
Yeah, and coffee is important.
Especially in a long contest like coming up this weekend. But yeah, the gunk stays here, and what you want makes it through the other side. So the stuff you want versus the stuff you don't want. So nobody wants to have grounds in their coffee. Or in a radio sense, we don't want noise in our receive audio. So first of all, talk about passive filters. Now a passive filter, the concept is that it's something that you put in a signal chain, and it doesn't require any power. It just filters by the nature of the coils and capacitors or the crystals or whatever is making up the passive filter. So it's passive components, capacitors, inductors, resistors, crystals, which we talked about last week. There's something called a mechanical filter, a couple different variations of this made by others. A little bit analogous to crystal filters. Then there's cavities, or cavity filters used for repeater duplexers. I'll be showing you a picture of that coming up. And passive filters always have insertion loss. They're not powered. We're running a signal through the filter, but in addition to getting rid of the stuff we don't want, we're losing a little bit of the signal because they're not powered. Now, active filters is the other flavor. These include an amplifying device, and usually the purpose of the amplification is just to make up the loss of the passive part of what a passive filter would be. Makes up for insertion loss. It might have a little bit of gain. Just some background. A crystal lattice filter is a filter for low-level signals made using quartz crystal. So we've got something here called a half-lattice filter, shown below. But what's interesting about it, notice how steep the skirts are. Since we've got two crystals involved, we've got they're peaked at slightly different frequencies, so we've got a fairly nice pass band between the skirts. So the crystals can't take a lot of power. You can't run a transmit watts through a crystal filter, for example. So it's low-level signals made using quartz crystals. And here's a couple of pictures. You'll see the terms ladder filter and lattice filter. Don't really need to know too much about why they're different, but there is an article here if you care to dig a little bit deeper. The ladder kind of looks like a ladder tipped on its side, and a lattice kind of looks like something that you'd put on your house to grow vines. So it's the physical layout. And in this case, you can see that, well, and there's just capacitors around. There's another type of crystal filter that uses switching diodes to change the characteristics of the filter, called a Jones filter, that we'll mention. So these are two implementations of crystal filters. Something called a helical filter. If you enjoy taking old radios apart, which I do sometimes, a helical filter is frequently used as a bandpass or notch filter in VHF and UHF transceivers. The reason it'd be VHF and UHF is that they've got to fit in a fairly small space. It'd be pretty hard to do this on 80 meters. The thing would be humongous. But just be aware of a helical filter. Then cavity, I mentioned this, typically used as on repeater sites. If you've been to repeater sites, you've probably seen some of these cans there. You might have wondered what those were, cavity filters. What it looks like inside, there's a plunger, which is a resonator, and that's adjustable. That's what this is on the top. And then it's got an input and an output coupler. And these are typically used in in the 2 meter band for repeater duplexers. So you can be transmitting and receiving at the same time. There's different classifications. We're going to get into this in more detail, but there's low pass, high pass, band stop, all different flavors. The concept of a low pass is that it passes frequencies below the cutoff filter, kind of like our anti-aliasing case we saw earlier. High pass will pass frequencies above the cutoff frequency. Sometimes we want that. Band pass will just give you a range of frequencies that you'll pass. Some of the IF filters in our receivers would be considered band pass filters. Band stop or notch filters. There's a function on many transceivers where you can turn on a notch filter to get rid of a carrier that's bugging you. Well, that's an example. And right, so now the cutoff frequencies, I'll have a diagram that show this. They're defined as 6 dB below the maximum, and I'll have a picture of that coming up. But just be aware for now that we've got all of these different classifications of filters. Kessler had a pretty nice animation on his site. Here we see a low-pass filter, meaning it'll pass the low frequencies and it will cut off frequencies that are above the cutoff frequency, also called the stop band. So the opposite of a low pass is a high pass, where it will pass the high frequencies but cut off the low frequencies. So it'd be a range of frequencies across the bottom, filter response vertically. And then if you put a couple of these together, you can have a passband filter where you're not accepting frequencies below the frequency of interest. You're not passing frequencies above the frequency of interest. Front-end filters on radios would be one example. And then the notch filter, where you'd be notching out a carrier that was bothering you, that's close to a frequency you want to hear, is a combination of a high pass and a low pass, just arranged so that you only get this, that you notch out the frequency that's offending. Now the shape factor, notice this is fairly steep here, and the shape factor is defined as the point where, okay, what we're passing is up here. Once we pass the filter corner, as this is called, and we're down 6 dB from that pass band, and then go down to 60 dB below, the shape factor measures a receiving filter's ability to reject signals in adjacent channels. And this is referred to as the filter's skirt. So the frequency ratio between 6 and 60 dB points is referred to as the shape factor. A shape factor of 1.0, a vertical skirt, would be perfection. And with digital filters, digital signal processing, you can get really, really close to a vertical skirt. That would also be called a brick wall filter, because frequencies just outside are going to hit the brick wall, and they're not going to get in. So shape factor measures a receiving filter's ability to reject signals in adjacent channels. Important to know. Some design definitions here. We've got, now the human ear isn't very sensitive to phase distortion, but some kinds of nonlinearities have a major effect in digital. So the shift of signal phase, now if we're dealing with coils and capacitors and designing and using filters, we're going to be getting some phase shifts due to the reactive components that are there. So shift of signal phase versus frequency between input and output isn't normally a problem with just voice communications. Linear response indicates smooth, no ripple as frequency changes, and I'll have a picture of that in the next slide. However, a nonlinear response can affect digital modes. Digital modes hate variations in filter phase. filter ringing. Sometimes if you use a really narrow filter, your radio might have a 3 kilohertz filter and a 1.8 kilohertz filter. If you go to CW, it might get down to 150 hertz. And the narrower you make the filter, sometimes it'll ring, meaning that the signal, it'll sound like there's a signal there at very narrow filter widths, undesired oscillations that continue after the signal is removed. So filter ringing is an effect that you can have with extremely narrow filters. Another picture of a mechanical filter here. And then filter types. There's several that are described here. These are all scientists. This one might have got its name from its shape, but let's just...
Dr. Elliptical.
Dr. Elliptical, yes, a PhD in elliptical things. So Butterworth, notice what we see in the diagram here. We've got very smooth passband. So digital signals would be really happy with this. A relatively smooth skirt and a smooth stop band. Now Chebyshev, notice that it's got a steeper skirt than the Butterworth. And butter, you think of butter as something that is smooth and you spread it on your toast, right? So Butterworth is smooth. Chebyshev has got a much steeper skirt, but it does have some passband ripple. So there's a trade-off there. Nothing is ever free. Then the elliptical filter is the sharpest skirt of these three, but it has ripples in both the passband and in the stop band. But each of these may be perfect for a given application. And you might be thinking, well, okay, this is nice. What if I needed a sharper response? Well, you can actually put a couple of these in series. You could have two Butterworths. That'd be a two-pole filter. You'd still have the smooth response, but the skirt would become steeper. And that's going to become important when we look at digital filters, because that's very easy to adjust the skirt shape in a digital filter. So with that as just an overview, let's see what the words say. Butterworth, passband, and stop band are flat. Okay. Now a couple things we'll need to remember. The Chebyshev, we've got ripple in the passband, but a nice sharp cutoff. Then the elliptical, I kind of like, if you could be drawing some ellipses on this picture and extend it over the whole graph, that is a good way you can remember what elliptical means. At least for me it was. Extremely sharp cutoff, one or more notches in the stop band, actually in the pass band too, but the pool only asks about the stop band. And then crystal filters, we've touched on a little bit already, used in receiver IF stages to get very narrow bandwidth, filter out adjacent signals. The bandwidth and response are determined by the crystal frequencies. So these frequencies, these crystals might be in slightly different frequencies, so they'll pass a broader passband. Now here's Mr. Jones. He was actually an engineer of one of our radio manufacturers in days gone by. Special type of crystal lattice filter with a variable bandwidth. It actually switch crystals on and off through the filter to adjust the bandwidth. And crystal lattice filters do find their application in sideband, but you don't run power through them. At a very low level, you can use them to filter out the unwanted sideband when you're developing single sideband before it's amplified. Here's a picture of a response of a quartz crystal. It's got very steep skirts at the resonant frequency of the crystal, very narrow passband. Signal source passes through the quartz crystal and you wind up with something like this. We showed some of these last week. Now we're going to switch to active filters. Remember, active filters are filters that are going to have gain, so they're going to be involved with an amplifier and feedback loops around the amplifier. They can be built without inductors. There's a lot of RC filters out there. I'll be showing you one. They have no insertion loss because the active device makes up the loss of the filter. Normally built with op amps. Of course, that would be relatively low frequency, but for audio applications, that's perfect. Gain and frequency are determined by external capacitance and resistance values. See kind of a small version of that here. Remember the feedback loop on an op-amp? Well, this one's got a capacitor in the loop. And there was a poll question last week that asked about that. A picture of the low-pass filter. You might be wondering, well, why would this vary with frequency? Well, recall that a capacitor is a reactive element, so its opposition to the flow of alternating current varies with frequency. That's why you can do these kinds of things. All right. Some things in context to the pool. Best suited for audio filtering and receivers. That's because op-amps are relatively low-frequency devices. Parts are cheap. And then a little factoid that you need to know, preventing op-amp ringing. Remember we saw that oscillators needed a feedback loop and gain. Well, that can be a problem if your op-amp starts to oscillate. So preventing op-amp ringing and audio instability in an op-amp filter, you can lower the gain, turn down the volume, and the Q. If it's not as sharp a filter, it'll be less susceptible to ringing. So with those words of explanation, hopefully this statement makes sense now. Preventing op-amp ringing and audio instability in an op-amp filter, restrict both gain and Q. And here's a schematic of one. This happens to be, it's called an active bandpass filter. It's active because there's a powered amplifier in the circuit. It's a bandpass because of the configuration of capacitors and resistors. And right on to some questions. We're doing great. Which of the following is most frequently used as a bandpass or notch filter in VHF and UHF transceivers?
Bravo.
It is a Bravo helical filter, and the reason that that's VHF and UHF is because that equipment, these helical filters are small enough to go inside the radio. Which of the following filters is used in a 2-meter band repeater duplexer?
Bravo.
Bravo, that's the cavity filter. Which filter type has ripple in the pass band and a sharp cutoff?
Delta.
That's the Chevy Chev. Yep, very good. Because the other types we didn't really talk about. We talked about Butterworth, but that doesn't have any ripple. That's very smooth. It's like butter. What are the characteristics of an elliptical filter?
Charlie.
It is Charlie. Extremely sharp cutoff with one or more notches in the stop band. Which of the following measures a filter's ability to reject signals in adjacent channels?
Charlie.
It is Charlie. Shape factor, you want it to be fairly steep normally. What is a crystal lattice filter?
Delta.
Yep, some of the other ones look tempting, but delta is the correct answer. The filter for low-level signals made using quartz crystals. How can unwanted ringing and audio instability be prevented in an op-amp audio filter?
Alpha.
Yeah, restrict both gain and Q, and they give you every combination here to help you get it wrong. So try to remember restrict both gain and Q. Okay, filters and impedance matching. All right, more different kinds of filters. Another picture. This isn't a coffee filter, but it's the same concept. For a digital noise reduction filter, we want the signal to pass through, but we do not want the noise to pass through. Just a concept. I really like this diagram. I found this after we had been teaching this for a couple of years, and this makes a lot of sense. These green boxes are delays. These are delays. So everything we've talked about before now have been analog filters with coils and capacitors or cavities or crystals, that sort of thing. Now we're advancing to digital filters. And some amazing electronics here. So digital filters are use digital delay elements in series with taps between the elements. So here's the delay elements. And then the taps, these are the places where we grab the signal. So at this point right here at T1, that's the signal that's being applied. T2 is delayed by one delay element, and so forth. So each Z is a delay. So we sum these outputs. we can pick them, turn them on, turn them off, and then we sum them. These are summing circuits to get an output. So the function of taps is to provide incremental signal delays for filter algorithms. And we see that working here. These are the delays. And then the digital signal processing is going to use those to create the filter shapes. So mixing of tap outputs determines performance, mixing of the outputs and the way that they're summed. And then if you want a sharper filter response, you need more taps. So you need to know the function of taps and the fact that if you have more taps, you can get a sharper filter response. Now we'll move on to two flavors of digital filter, the FIR and the IIR, which is the finite impulse response and the infinite impulse response. You might be wondering what an impulse is. Well, that would be like just a sharp signal that just is there momentarily, and then how the filter reacts to that defines its characteristics. But that's what impulse means. So finite, this is an example, the one that we saw already. You'll see that the signal comes in here, comes out here. The characteristic is that it can delay all frequency components in the signal by the same amount. Basically what comes in, it's going to be modified here, but what comes in here is going to be what comes out there. So it can delay all frequency components of the signal by the same amount. Finite decay time, so if a signal starts here, once it gets all the way through, it's done. There can't be any ringing. Now the infinite impulse response, now look how much more complex this looks. We have our delays again, we've got our taps again, but we have some feedback loops here. Out of this chain, we've got a feedback loop coming into a summer, summing the signals. We've got another feedback loop here. So this can go around and around in circles. So this behaves more like an analog filter, and the decay time can be considered to be infinite. Well, we know it really isn't infinite. It's like Kessler showed when he tapped a glass, that you could hear the glass ring, but it very quickly decayed to not being able to hear anything. Well, in theory it can be infinite, but it does have a decay time. So two different flavors. One is straight through, one depends on feedback. It's a little bit closer view, input signal samples. This matches the diagram we showed before. These taps, which are also called coefficients, wind up being summed and then go to the output. Now it looks like we've only got 3 taps here, 1, 2, 3. So, but the fourth is the original input signal. That's why it's a 4-tap filter. The infinite impulse response, just a different view of what we showed before, have some feedback loops. We've got the same delays in the signal, or here and here rather, but then we feed back in this case. So 3 feed forward taps and 2 feedback. So these are the feed forward, and these are the 2 feed back taps. So those can be combined in all different ways, and this will act a little bit more like an analog filter. It all depends on your design goals. Why would you use one versus the other? Depends on what you want to use it for. Now there is one problem that comes from digital filters. In each one of these delays creates what's called latency. It takes a little bit of time to process through those delays. And that can be a serious problem. And smart digital designers have found ways to minimize those, but that is a potential feature. It can be a feature, but it's usually more of a bug. Latency, so video could sound out of sync. Bluetooth headsets might not be in sync with the audio. I had an interesting summons on the air activation where I was trying to use a Bluetooth headset, and my transmitted signal made me sound like I was an absolute beginner, a total lead, because what I was hearing in my ear was not what I was sending on the key, especially with dots. So that was an example of latency with Bluetooth, and I finally figured out what it was and turned off the Bluetooth headset and went back to a conventional headset. Gary has a comment too.
Well, I was just going to say, on Flex Radio, they've, in their smart SDR software, have made adjustments to their receive filters where users can adjust how sharp they want the filtering, knowing that they're going to give up some latency, so you can adjust it. Contesters, they want to be right there, right now, with their transmissions and receptions. They don't want to be milliseconds after the other guy who's calling.
Yep.
So that can be important.
Yep, absolutely. That comes with the territory with digital filters. All right, there's a couple of other factoids here. More on digital signal processing. Adaptive processing, that's where you can distinguish voice content from noise content. Software can recognize and adapt to the signals and conditions. They're automatic, they don't require any tuning. Adaptive filter used to remove unwanted noise from a received signal sideband signal. That would be like the noise filter button on your radio. So you can build filters digitally that are completely impossible with pure hardware. I mentioned the brick wall filter, extremely sharp cutoff or skirts, can approach a shape factor of 1.0 in digital. And some questions. What kind of digital signal processing audio filter is used to remove unwanted noise from a received single sideband signal?
Just talked about it.
Yeah,
Adaptive.
it was on the previous slide, alpha and adaptive filter. It's amazing how it can tell the difference, but it can. Which of the following is generally true of finite impulse response filters?
Alpha.
It is alpha. FIR filters can delay all frequency components of the signal by the same amount. I commented that what goes in on one end comes out on the other end, including all of the frequency components. Good way to remember that. What is the function of taps in a digital signal processing filter?
Delta.
It is delta. Provide incremental signal delays, and then those delays are used for the filter algorithms. Which of the following would allow a digital signal processing filter to create a sharper filter response?
Bravo.
It is Bravo.
Bravo.
More taps, exactly. Good. We survived that. This was a difficult area in some of our past classes. Impedance matching. All right, so I'm going to give you a couple of tricks here that will help you with all of the pool questions. The memory tricks are really stupid, but if you'll bear with me, I think you'll say thank you when we're done, okay? So bear with me. So impedance matching. Now we want the load and source impedance to be equal if possible, because if they're not, an impedance matching network is needed. Otherwise, you'd be losing a lot of your signal. So you want 50 ohm transceiver, 50 ohm transmission line, 50 ohm antenna if possible. That's perfect impedance matching. So how an impedance matching circuit transforms a complex impedance into a resistive impedance. How does it work? And here's a picture of one. It cancels the reactive portion of the load impedance, and it transforms the resistive component to the desired value. So the reactive component would be like if you had a value, you remember back from our complex impedance discussions, 50 plus J25, well, you'd want to cancel the plus J25 to 0 and cause the, also alter the resistive value so that everything was matched. So I'm hoping that this will make sense now. Cancels the reactive portion of the load impedance, either inductive or capacitive, and then transforms the resistive component to the desired value. And here we're showing a 50 ohm transmitter, 50 ohm transmission line, 50 ohm antenna. Maximum power transfer when all elements have equal impedance. That's why when we want to do impedance matching. Now where do we, here's a picture of, now the antenna tuner that is shown here, that's the combination of coils and capacitors that makes the transmitter think that it's seeing a 50 ohm antenna. It might not really be. What's called an antenna tuner is really matching the transmitter to the antenna system. The antenna might be 200 ohms, the transmission line be 50, so we've got a mismatch there, and the transmitter is going to see something that's really whacked out. So that this is typically where they go. These dotted lines are the wall of your ham shack. This is outside, this is inside the shack and outside. So this is commonly where they're placed. And an antenna tuner can also be placed out at the antenna with differing results, but there's pluses and minuses to doing that. This is what you would normally see. So here's a visual of an antenna tuner. It's got capacitors and a coil and a switch to pick different taps of the coil. So now we need to consider how can you recognize from the circuit diagram if it's a high pass or a low pass? I'm not quite to our memory trick yet. I'll just explain what we're doing first. When we have as a series element, now notice in this case we've got a transmitter, AC generator, and the series element is a capacitor in series with the load. So high pass, we have capacitor or capacitors in series, which passes the high frequencies, while the inductors shunt low frequencies. So whatever we have as the pass element, in this case a capacitor, we're going to have the opposite as the shunt element. Capacitor up here, inductors down here. All right, so this is the high pass configuration. This is the low pass configuration. Notice that the pass element is now an inductor and the shunt elements are capacitors. Whatever this is, the other one's going to be the opposite. So low pass inductors in series passes the low frequencies while capacitors shunt the high frequencies. So these are the two configurations, high pass and low pass. Going to be important. So we've got filter configurations. Next, we've got pi. You can kind of see that this looks like the letter pi. We've got an L. It looks like an L. This would be a low-pass filter, inductor in series. This is a T network. This is going to be a high-pass filter. We have capacitors in this series. And this is a pi L. This is basically a pi here, but with an additional inductor on the output. That's a pi L configuration. Okay, here comes the memory tricks that I promised you. So look at the series element. By series, I mean from the source to the load. In this case, there's an inductor in series. So look at the series element. And then for a capacitor, think of the capacitor as a hurdle that you have to jump over. If you have to jump over it, it must be a high, you have to do a high pass over the filter, right? Again, kind of a stupid little thing, but it'll work. For a low pass, think of a limbo bar. You must go under or pass under it, low pass. So if that helps you, there's no additional charge for that. And there's about I think 3 or 4 pool questions that you'll get all tangled up if you can't remember which one is which. So that's why I share these things. All right, so here's the kinds of the networks. All right, and the characteristics you need to know about. So here's a low pass pi. Low pass, because we've got an inductor. I go under the limbo bar. Low pass pi. Capacitor. Now, the easiest way to think of this one is to identify the series element first. And they really confuse you because they talk about the shunt element in the first part of the answer. So I'll read it and then come back to it. A capacitor is connected between the input and ground, and input and ground, right. Another capacitor is connected between the output and ground, that's this one, and an inductor is connected between the input and the output. So my recommendation is find the series element first, okay? And then you'll know that it's a low pass, and it's obvious that it kind of looks like the letter pi. And then hopefully it'll make sense. We've got this identified, therefore the capacitors have to be what they're talking about up here. So hopefully that makes sense now. A capacitor is connected between the input and ground, another capacitor between the output and ground, and an inductor is connected between the input and output. The rest of them are a little clearer. A pi L network, down here, is a pi network with an additional inductor on the output. It doesn't ask us if it's a low pass. It is, because it's inductors. But in addition to the pi configuration, we have an additional inductor on the output. Well, why would we want that? The purpose of adding an inductor to a pi network is to create a pi L network for greater harmonic suppression. So if you're transmitting on 40 meters, you don't want to be also putting out harmonics on 20 meters. And this would help prevent that. The frequency response of a T network, that's over here, with series capacitors in a shunt inductor, is a high pass. They kind of arrange these words in all different orders to help confuse you, but you can see right away if we're talking about a T network with series capacitors, the series element is a capacitor or capacitors, so it's going to be a high pass, and then shunt inductor. Whatever the pass element is, the shunt element will be the opposite. So that's why I said those silly little memory tricks would help you with multiple answers. And here we are. See if we can remember that. How are the capacitors and inductors of a low-pass filter pi network arranged between the network's input and output? All kinds of confusing words, but if you kind of picture in your head what they're talking about in the question, the answer hopefully will jump out at you.
Alpha?
Delta.
No, it is delta. Delta. Yeah, capacitor connected between the input and ground, another capacitor between the output and ground, and then they put the pass element at the end of the answer. An inductor is connected between the input and output, making it a low-pass filter. What is the frequency response of a T network with series capacitors and a shunt inductor?
High pass.
It's going to be a high pass.
Bravo.
Yep, bravo. What is the purpose of adding an inductor to a pi network to create a pi L network?
Alpha?
It is alpha, yep, greater harmonic suppression. We have an extra element in the filter which will work to reduce harmonics. How does an impedance matching circuit transform a complex impedance to a resistive impedance?
Charlie.
It is Charlie. It cancels the
Charlie.
Yes, correct. It cancels the reactive part of the impedance and changes the resistive part to the desired value. So that's very often used in what are called antenna tuners. What describes a pi L network?
Oh, that's easy. Bravo.
There you go, yes, pi network with an additional output series inductor. And if you go back to the diagrams and what I call my stupid memory tricks, I think this will all lock in for you. Now we get to power supplies. Power supplies are very interesting. We have to have power supplies to make most of our radios work. If you buy an ICOM 7300, you've got a really nice radio, but it won't do anything unless you hook it up to some kind of power. That could be a battery in your car, but most people, a lot of people will start with that as their main station radio. So they need a power supply to power the radio. It needs to be 13.8 volts typically, and capable of, if you've got a 100-watt transceiver, it need to be able to generate about 23 amps of power at 13.8 volts DC. Those two flavors, there's a shunt regulator and a series pass regulator. There's only one pool question about the shunt regulator, and Kassler mentioned that we usually never see this in a transceiver configuration because the power supply has to be putting out 23 amps all the time. And there's no such thing as a Zener diode that can handle 23 amps that burn up. But for some low voltage circuits, a shunt regulator could be used. But because there is a pull question, we need to know the difference between a shunt and a series pass, and that these exist. Now, the ones that you'll see in just about all of the power supplies that you're going to run across will have an input. I called this 25 volt DC input. That'd probably be from a transformer and rectifier. And then a series pass device, which is a transistor that will pass only the voltage that the radio needs. And how does it know that? Well, it uses a Zener, not in this configuration, but it just uses the Zener diode as a reference voltage to the base of the transistor, so that as the radio draws more current, it knows that it has to increase the amount of current that it's conducting through the transistor to hold it to that reference voltage. So that 13.8 volts will be maintained rock solid from receive to full 100 watts output transmit. This is highly simplified, of course, but we'll add some nuance to it as we continue. Now the shunt regulator, there is only one pool question, and it operates by loading the unregulated voltage source. So it has to pass the full current through this path all the time to maintain this voltage going out. So it operates by loading the unregulated voltage source. This is the unregulated voltage source, the input, and the output. And of course, that's very inefficient. Maximum current flows all the time, so the power is wasted that's generated as heat here. Now, a whole bunch of pull questions about the series pass voltage regulator. So 25 volt DC input, 13.8 volts output in her Zener for a reference. So how a linear voltage regulator works. The conduction of a control element, well, why couldn't they just call it a transistor? But this is how it's in the pool. How a linear voltage regulator works, the conduction of a control element is varied to maintain a constant output voltage over a wide range of currents. Q1, which I said was the pass transistor, controls the current to keep the output voltage constant. Q1. The pass transistor maintains constant, and I said output, constant output voltage over a wide range of load current. So the transceiver might go from 500 milliamps to 13 amps from receive to transmit, for example. So it's going to hold that right at 13.8 volts. And then the Zener diode is used as a stable voltage reference. Lots of pull questions there, all on this one circuit. And here's our circuit again. We're going to talk about several aspects of it. I think this is pretty similar to what we saw previously. So they ask about what certain circuit elements are used for. So this overall circuit is a linear voltage regulator. Linear because it continuously adjusts the load to be at its stated value. It's marked as 12 volts here. Q1 controls the current supplied to the load to keep the output voltage constant. So they're going to ask about what are these specific components used for. That's the the nuance that's being added to the pool questions here. C1 they don't ask about. It's a filter capacitor. C2 they do ask about. It says it bypasses the rectifier output ripple around D1. Now, because a transistor is also an amplifier, if there was any hum on the base, you wouldn't want that to be superimposed on the output of the transistor. So C2 bypasses, if there's any impurities here from the source, it'll bypass those around the diode so that it won't affect the reference for the linear voltage regulator. C3, they don't ask about. Prevents self-oscillation. R1 from 25 volts supplies a reference, or supplies voltage to the zener. R2 provides constant minimum load to Q1. Again, they don't ask about that, so you just have to worry about the ones they're going to ask us about. In the D1, this is a zener diode which provides a stable reference voltage over wide-ranging current that the transceiver may need. Now, because this, you can kind of see it's 3 terminals, an input, output, and ground. Remember we talked about 3-terminal devices last week? Well, a regulator can be packaged that way. So all of this electronics can be put in one little package. So this is a 3-terminal voltage regulator, is a series regulator. Of course, you couldn't run a transceiver from this, but you could provide a very low level of stable voltage out of it. Now, this one has been very confusing to people in the past, so I'm going to walk through it. Now, we've got the input over here, the output over here. Now, notice the difference. We got 25 volts, we got 12 volts. The difference is 13 volts, okay? So there's going to be 13 volts dropped across the transistor. Now, there's a definition here for dropout voltage. At some point, if for whatever reason this input voltage would get lower and lower and lower, eventually it would get low enough so that the poor little transistor wouldn't be able to hold it up to 12 volts. I don't know if that would be 13 volts or 14 volts, but at some point in time, the transistor would stop regulating the minimum input to output voltage required to maintain regulation is that definition. Next is another one. Let's assume that 2 amps of current is flowing for whatever load it is that we're needing. Maybe the receiver is on and the volume is turned up all the way. So the formula for calculating power dissipated by the series linear voltage regulator, it's the voltage difference from the input to the output, that's our 13 volts, multiplied by the output current. So remember our pi formula, power equals current times voltage? That's what this is. In this case, 13 volts times 2 amps is 26 watts. So the transistor would have to be capable of dissipating that amount. Quite often you'll see past transistors in a power supply heat sinked to an aluminum heat sink to dissipate that heat. But you need to know these blue words. They're not going to make you calculate it. Let's see if the blue words make sense now. Formula for calculating power dissipated by a series linear voltage regulator. Voltage difference from input to output multiplied by the output current. So those are the words you need to remember. Battery. This is kind of a simple concept. In this case, we've got a 12 amp hour battery. Amp hours, okay, that says you could supply 1 amp for 12 hours. Well, what if you were only needing half an amp? Well, that would last for double that amount, or 24 hours. What if you needed to supply 2 amps from this 12 amp hour battery? Well, it could last for 6 hours. See how that relationship works? So operating time is the amp hour rating of the battery divided by the current that's being drawn, or the average current. Thus, battery operating time is calculated by the capacity in amp hours divided by the average current. So a small transceiver might work for days. Little QRP. A bigger one might only work for an hour or 2. Then we've got switch mode power supplies. These are interesting. This is a common ham switch mode power supply. 13.8 volts, 30 amps, it weighs 3 pounds. Here's another one. This is what's called a linear supply, 13.8 volts. In this case, it's 35 amps. It weighs 10 times as much, 29 pounds. So big difference. So the switch mode is the little guy here, but it puts out the same amount of current. All right, how does it do that? Well, it varies. It works by varying the duty cycle of pulses to a filter, which by itself doesn't make any sense, but I'll show you a picture. Now, the pulse duty cycle is controlled by feedback from the output voltage, holding the output voltage constant. So it's sending pulses to its internal pass devices, if you want to call it that, causing the voltage to stay constant. It's less expensive. A switch mode power supply is less expensive and less weight because it's running at a higher frequency. The linear is running at the 60 cycle AC current that you get from plugging into the wall. The switch mode takes that 120 volts and converts it to a much higher frequency, maybe 10 kilohertz, 15 kilohertz, or even higher, and then all of its internal electronics runs from that frequency, requiring smaller transformers and filter components for equivalent power output. Now let's see if this makes sense now. Less expensive and less weight. High frequency inverter design uses much smaller transformers and filter components for an equivalent power output. Okay. And then a third pool question. Switch mode power supplies may generate interference. Oh, that's bad. That appears as a series of carriers at regular intervals across a frequency range. Now, because of this, because they're using this switching effect, that generates square waves, which generates RF noise. Now, switch mode power supplies designed for ham radio have taken this into account and are really pretty clean. You can trust them. So if you have a switch mode power supply that you buy from DX Engineering, it's going to be fine. If you have some Chinese thing, or if you're trying to use a power supply from another source, you got to be careful because that might make this noise. Some hams are strongly biased in favor of only using linear power supplies for this reason. But these work just as well. They're much less expensive, and they're very clean if they're designed for ham radio use. The picture of a power supply, switching power supply. So it connects directly to the 100, I'm using 120, it's different in different parts of the world. Some people have 240 volt supplies coming in, but I'm using 120 just for an example. So we go right from, no transformer here, we're going right from the 120 out of your wall and immediately go to a rectifier and filter. And then there's a chopper here that chops up that DC voltage. There's an output transformer. The output rectifier and filter then supplies power to your radio. But there's a feedback loop here saying if we want 13.8 volts, we're going to control this chopper in a way, it's called pulse width modulation, that will control how much gets through to maintain this 13.8 volts. And then there's an article here if you want to dig a little bit deeper, but that's a high-level view of how it works. Now we're going to look at high voltage power supplies, and you might be wondering, why would we be concerned with a high voltage supply? Well, if you've got a high power amplifier, 1500 watt amplifier, it may be a tube operated amplifier and it's going to need high voltage, possibly several thousand volts. So the output of the circuit will usually have to be filtered, done with capacitors. The capacitors may be connected in series to add up to the needed voltage, because if it's a 1,000 volt power supply, you might not be able to find capacitors that are 1,000 volts, but you could find 450 volt capacitors and put them in series. So connecting resistors across series capacitors does three things. Equalizes the voltage drop across each capacitor. It serves to discharge the capacitors when the power supply is turned off, the voltage is removed, and provides a minimum load on the supply. Those three things sound like an all of these question. And then there's something called a step start circuit. When you first turn on a power supply like this, there can be a large inrush current which could blow fuses, okay? So a step start circuit starts it off slowly and then brings it up to full voltage. So it allows filter capacitors to charge gradually. Here's a picture of some electrolytic capacitors in series and the resistors across them. It's a picture of a step start circuit. So we start out with a resistor in series with the transformer, and then after a certain number of milliseconds, this relay will pull in, and you'll get the full voltage across the transformer, and the power supply will go to full voltage. All right, how does a linear electronic voltage regulator work? You hear silence. What do you-
Delta.
It is delta. The conduction of a control element, which is a transistor, pass transistor, is varied to maintain a constant output voltage. What device is used as a stable voltage reference?
Alpha.
It is alpha, a Zener diode, exactly. Which of the following describes a three-terminal voltage regulator? Remember I said you could put all of that.
Charlie.
Well, okay, the three-terminal voltage regulator is putting all of that electronics into a three-pin package series regulator.
I'll be messing that one up.
Yeah, well, think about it, or go back over it. Which of the following calculates power dissipated by a series linear voltage regulator?
Charlie.
It is Charlie. Good. Glad you got that one. It's we changed how we presented that to help people get it. Which of the following types of linear voltage regulator operates by loading the unregulated voltage source?
Yeah. That's the shunt.
Yeah, this is the oddball and the
Shunt.
only question
Delta.
that relates to that, delta. What is the purpose of Q1?
Charlie.
It is Charlie. Controls the current to keep the output voltage constant. What is the purpose of C2?
Alpha.
It is alpha. Bypasses the rectifier output ripple around D1. What type of circuit is shown here?
Charlie.
Charlie, that's our linear voltage regulator we've been talking about. What is the dropout voltage of a linear voltage regulator?
Charlie.
It is Charlie. Minimum input to output voltage required to maintain regulation. How is battery operating time calculated?
It's easy.
Yep. It's easy, but what's the answer?
Charlie.
Charlie, capacity in amp hours divided by the average current. How does a switch mode voltage regulator work?
Bravo.
By varying the duty cycle of pulses input to the filter, also known as pulse wave modulation. Why is a switching type power supply less expensive and lighter than an equivalent linear power supply?
Charlie.
It is Charlie. The high frequency inverter design uses much smaller transformers and filter components for equivalent output. What causes interference received as a series of carriers at regular intervals across a wide frequency range?
Alpha.
Correct. Switch mode power supplies. We're almost done. What is the purpose of connecting equal value resistors across power supply filter capacitors connected in series? Read carefully.
Oh, that's easy.
Delta.
It is
Delta.
delta. All of those answers are correct. What is the purpose of a step-start circuit in a high voltage power supply?
Delta.
Delta to allow the filter capacitors to charge gradually. And that is the end. Yeah, we kept you 50 seconds over, so you get paid overtime.
Dang.
You get paid
Dang it.
overtime for that. All right. Well, we'll close there unless anybody's dying to ask something.
Now, next week, chapter 7,
Yes.
we're going to expand on some of the concepts that Dave talked about as far as signals and measurements and specifications. So all of those specs you read in the ads, we'll try to demystify some of those.
Very good.
But they've been good. Let's let them go home.
Yes.
Oh, wait, they're already home.
Yeah, for sure. Wish I was. All right, we'll see y'all.
Till next week, y'all.
Thank you.
73.
Thank you.
73.
65.
72 is what QRP guys use because they don't have enough power to get up to 73. True story. That's what they